Hello there, welcome to your Lecture 11 skill check, all about one-way ANOVA. So first let's look at the scenario. Here, again, it's a pretend scenario where we're imagining that Dr. Helen Sharp, who is the chair of hematology and medical oncology at the New Amsterdam Public Hospital, we're imagining that she conducted a double-blind clinical trial with new treatments by randomly assigning 50 patients each to 4 groups. The first group received a placebo, while the remaining 3 groups received 3 different treatments. After 6 months, a quantitative health outcome was measured for each patient where positive values indicate an improvement in their condition. So what can we take out of this description that is important for our analysis? Well, first of all, we can see that we have 50 patients, each randomly assigned to 4 groups. So given that we're dealing with groups, that's telling us that we have one categorical variable in this scenario. It's also good to note that it's a double-blind clinical trial. That doesn't matter very much in terms of the analysis of variance, but the concept of a double-blind clinical trial is something you learned in 2208. So if you don't remember what that is or why it's important, you can always check that out. So we have 4 groups. We also have, let's see, all right, the groups are receiving different treatments. One group receives a placebo. Each of the remaining 3 groups each receive a different kind of treatment. And we have a quantitative health outcome. So we have a categorical variable and a quantitative variable. This is one of the conditions for the one-way analysis of variance, the one-way ANOVA. So question 1 was to list the independent and dependent variables and state the null and alternative hypotheses in the context of this scenario. So the independent variable, or the predictor, is the treatment a patient receives. So we have placebo, treatment 1, treatment 2, treatment 3. Clearly, that's categorical. We have a dependent variable or response, which is the quantitative health outcome. The null hypothesis is that the population mean response for each of these 4 groups is the same, and the alternative naturally is the opposite. It's that the population mean responses are not all the same. Or you could say that at least one of the population mean responses is different. Now, so this plot I didn't give you on the PDF for this skill check, but I thought it was a good idea to show you this plot anyways. So what we're seeing here are the box and whisker plots for each group of 50 patients at the end of the clinical trials. So we have our placebo group and our 3 treatment groups. And so a couple things you can see here. One is you can see that the spread or variance of these 4 groups are roughly the same, and that's a good thing to notice, because that's one of the conditions we need to check in order to conduct our one-way analysis of variance. The second thing you might notice is that the mean values, which are indicated by these squares, these mean values are not all the same. So we have some variation in our data due to differences in the mean values between groups. Now, here is an important concept. It's true that these sample means are different, but that does not imply that the corresponding population means are different. And why is that? Well, it may be that the differences between sample means that we can see in this plot, they could be due to nothing more than sampling variability, and the population means in truth could all be the same. We don't know. This is the precise reason why we need to conduct our analysis of variance. We need to find out if the evident differences between these groups is something real, meaning that the population means are actually different, or if it's just a product of sampling variability. So how can we tell whether the population means are different? We must compare the variance between groups, which would be the variance caused by differences in group means, to the variance within groups. That's what analysis of variance is all about. Okay, question 2. It appears that the conditions for one-way ANOVA are satisfied. State each condition and explain why it is satisfied. Well, the first two conditions are quite straightforward. They don't require looking at a plot. We need to know first that we have one categorical predictor variable and one quantitative response variable. This we've already confirmed. The predictor is the type of treatment a patient receives, and the response is a measure of the health outcome. So we have that. We also need to note that the patients are randomly assigned to groups. That implies independence. So we have our independence assumption is satisfied. Now what we need these graphs for is to confirm the remaining two conditions that are required. First, we need to look at the residual versus fitted values to see whether it appears that each group has the same variance, or to put it more simply, the same spread. And that's pretty clear. You can see we have these four groups, and the spread in the vertical direction is very much the same for all four groups. So the equal variance assumption for the residuals, that equal variance assumption is satisfied. And finally, we look at the normal probability plot. And just please remember that the only thing this plot is good for is to assess whether the residuals are approximately normal in distribution. Here we can see that is the case because these points for each residual are lined up very nicely in a straight line. So that is indicating we have a very, very nearly normal residuals. And so that condition is satisfied. So now that we know all our conditions are satisfied, then we can go ahead and conduct our analysis of variance. So question 3, here we're going to fill in missing values in the ANOVA table. So one thing that I think is pretty cool about ANOVA is once you have the sums of squares for the factor and the error, and also knowing what the scenario is, so how many groups you have, how many measurements you have, when you have that information, you can fill in this table. And so that's what we're going to do here. So starting with degrees of freedom. The degrees of freedom for the factor is just 1 minus the number of groups. And so here we have 4 groups, meaning that the degrees of freedom is 3 for the factor. The degrees of freedom in total, I'm going to hit next. That's easy. That's just the total number of measurements minus 1. So we have 4 groups, 50 people in each group. That means we have 200 measurements in total. And so the degrees of freedom for this total is just 200 minus 1. It's 199. So that's easy. Now for the error, the easiest way to think about it is the factor degrees of freedom plus the error degrees of freedom must add up to 199, and so the number under this square must be 196. Another way to remember that is the error degrees of freedom is the number of observations minus the number of groups, also 196. So next we're looking at the total sums of squares. It's important to remember that sum of squares is a measurement of variation. So here we're looking for the total variation, a quantification of the total variation of the data. So the total sums of squares, this variation, is just equal to the sum of the variation due to the factor plus the variation due to the error. And so that's easy. We just add those two numbers together and we get 76,184. Now, oh right, I forgot I was going to say this. So remember, the total variation is equal to variation due to differences between group means plus variation due to differences between individuals within groups. I think the sort of the central concept in analysis of variance is basically this, is to understand we have two sources of variation. One, differences between groups. Two, differences between individuals within groups. Right, so now we look at the mean sum of squares. And here we're making a distinction then between what we call variation and over here what we call variance. So the mean sums of squares are measures of variance. So the variance is easy. You just divide by the degrees of freedom. And so in the first case, the mean sum of squares for the factor, or in other words, the variance for the factor, is just equal to the sum of squares for the factor divided by the degrees of freedom. It's the variation divided by degrees of freedom. And so that's just 10,710. And likewise for the error. Right. So before I get to that, remember that the mean sum of squares for the factor measures variance due to differences between group means. Now continuing to the error, again we just divide by degrees of freedom, so we take the variation attributed to those errors, to differences within groups, and we divide by the corresponding degrees of freedom. We do that, we get 224.8, and here remember that the mean sum of square of error measures the variance due to differences between individuals within groups. Right, so finally, to conduct the actual test, we need to calculate our test statistic, and it is simply a ratio of variances. And that's kind of why this method is called analysis of variance. So we're looking at the variance due to differences between groups, so to the factor, to differences in the treatments that each patient receives. And we're dividing by the variance attributed to individual differences between people. And so when we look at that, it's simply 47.65. And I just noticed that I didn't put any numbers here, but you can see that 47.65, it's going to be this number, 10,710, divided by 224.8. That's where this F statistic comes from. The p-value for this F statistic is very large. Sorry. The F statistic itself is very large. The p-value is therefore very small. And that is indicating that we have evidence that some of those population mean responses are different. So in other words, it's clear that we're going to wind up rejecting the null hypothesis. Now, let's just look at that a little bit more closely. Right, so before we do that, question 4, we're asked to calculate the coefficient of determination. And so this is the same coefficient of determination that we saw when we did linear regression. And it's calculated exactly the same way. We're going to be looking at these measures of variation, looking at the sums of squares, and we're going to compare the sums of squares that it's attributed to that predictor variable, or factor, if you will, divided by the total variation in the data. And so that's simply a ratio of these sums of squares, and that turns out to be 0.42. So what does that mean? That means that 42% of the total variation in the 200 observations is explained by differences in treatments: placebo, treatment 1, treatment 2, treatment 3. And that, by the way, is a very large proportion of the total variation. And that sort of is consistent with the fact that we have a large F statistic and a very small p-value. Okay, so now returning to talking about the p-value of this analysis. Here we're going to use the F table. We're going to find the approximate critical value, and then we're going to use technology to calculate the exact p-value, and then we can draw conclusions. So we have to go to an F table for this part. And notice here we're using an F table for a 1% test. Why? Because the question asked us to find the critical value for a 1% test. And so here our F statistic has 3 and 196 degrees of freedom. 3 corresponds to the degrees of freedom on top of the fraction. So that's 1 minus the number of groups. And 196 is the degrees of freedom for the error on the bottom of the fraction. We can't find 196 on this table, and so we have to use something as close as possible without going over. That's 180. And so the critical value is 3.89. So what do we do with that? Well, we have our critical value for a 1% test. We have our test statistic. If we were to sort of sketch what the distribution looks like, we can see, of course, the F statistic is much, much bigger than the critical value. And so we can reject the null hypothesis at the 1% level of significance because the test statistic is to the right of the critical value. Rejecting the null hypothesis means that we're going to conclude that of those 4 population mean responses, at least one of them is different from the rest. Now let's talk for a minute about what the p-value is. The table gives a p-value of 0.000. If we want it to be more precise, we could use technology. And so one easy way to do that is to find a web page for which you can simply plug in your F statistic, your numerator and denominator degrees of freedom, and you press a button and you simply get a p-value. So in this case, the p-value is less than 1 part in 100,000. So it's a very, very small p-value. Okay. So what does that p-value tell us? It tells us we have very strong evidence against the null hypothesis. So to answer this question 5, we would say first, the critical value for a 1% test is 3.89. Our test statistic is 47.65. It's very much larger than this, and the p-value for the test is very much smaller. So the conclusion is the ANOVA indicates that at least one of the population mean responses is different from the rest. Right, so now the final thing you would do in the analysis of variance, once you conclude that at least one population mean is different from the rest, you then need to figure out which of them is different. And so this is where the multiple comparisons come in. Now notice here we had 4 groups. That gives us 6 comparisons in total, which you can see in this table. So let's just divide this table in half for now and look at the top half. What are we seeing here in the top half? What we're seeing are 3 statistical tests that compare the treatments, each treatment, to the placebo. Now I want to emphasize that each of these tests, each of these comparisons is a 2-sample t-test. And what do we do with a 2-sample t-test? We test whether or not 2 population mean responses are different. And so looking at this first row, we're comparing the population mean response for treatment 1 against the population mean response for a placebo. What we see over here is a simultaneous 99% confidence interval for that comparison. So this is a confidence interval for the difference between population mean values, treatment 1 compared to placebo. And what can you see here? This interval contains only positive values. That is an indication that treatment 1 is giving a higher mean response than the placebo. And that's confirmed by the p-value. The p-value is very small. And so here we're going to reject the null hypothesis of the 2-sample t-test and conclude that the population means are different, and moreover that treatment 1 has a larger population mean than the placebo. So we can look at all 3 of these comparisons and we can see that the same story applies in each case. And so what that means is that the data provides evidence that the population mean response to all 3 treatments is greater than the population mean response to the placebo. We can tell because 1, all 3 confidence intervals contain only positive values, and 2, all 3 p-values are very small. Okay, so now let's look at the bottom half. Here we're comparing treatments with one another. And so in the first instance, we can see if we compare treatment 2 with treatment 1, this 2-sample t-test is giving us a confidence interval for the difference between the population means that contains only positive values. Furthermore, the p-value is very small. This is indicating that the population mean for treatment 2 is greater than the population mean for treatment 1. So the data provides evidence that the population mean response to treatment 2 is greater than the population mean response to treatment 1. We can tell because, first, the confidence interval for this comparison contains only positive values, and 2, the corresponding p-value is very small. Continuing with the third comparison, here we can see that the confidence interval contains only negative values. What does that mean? Well, that tells us that the population mean for treatment 3 is evidently less than the population mean for treatment 2. That's why we're having negative values. The difference between these population means has a confidence interval that contains only negative values. The p-value is also very small. And so we can say that the data provides evidence that the population mean response to treatment 3 is less than the population mean response to treatment 2. We can tell because first, the confidence interval for this comparison contains only negative values, and second, the corresponding p-value is very small. Finally, there's the treatment 3 versus treatment 1. Here, the confidence interval contains 0, and the p-value is quite large. So here, we can say that the data provides evidence that the population mean response to treatment 3 is no different than the population mean response to treatment 1. We can tell because first, the confidence interval for this comparison actually contains 0. And so 0 is a plausible value for the difference between those two population means. And 2, the corresponding p-value is greater than 0.0019. Now, you might be wondering, where did I get this number, 0.0019? Well, this is the level of significance for each of these 6 two-sample t-tests. And how do I get that number? Well, if you look down here, we can see that the individual confidence level is 99.81%. And so what that means is each two-sample t-test is conducted at the 0.19% level of significance. And just remember that the ANOVA itself, that test itself was conducted at a 1% level of significance. And so each individual comparison must be conducted at a smaller level of significance to control the false positive rate. Now, so here we reject the null hypothesis that the two population mean responses are equal only if the p-value is less than this number. And so if you look at 2 versus 1, the p-value is much less. 3 versus 2, the p-value is less, but 3 versus 1, the p-value is greater than 0.0019. And so here we fail to reject the null hypothesis, consistent with the fact that this interval contains 0. So here is another diagram I did not include in the PDF for the skill check. And part of the reason is this. When you get the final exam, when you're asked a question like this one, and you're asked to make conclusions from the multiple comparisons, you might be given a table like we just saw, or you might be given a diagram like this. I don't know which you're going to be given, so you need to understand how to interpret both. You'll probably agree that using the diagram is quite a bit easier. Here we can clearly see that each treatment is better than the placebo because the confidence interval for the difference between those population mean responses, all of these confidence intervals are on the right side of 0. They all contain only positive values. Whoops, I guess I wasn't ready for that. Right, so you can also see down here when we compare treatments, treatment 2 is clearly better than treatment 1 because this confidence interval is on the right of 0. Treatment 3 is worse than treatment 2 because the confidence interval for that difference between population mean responses is on the left of 0. And then treatment 3 and 1 aren't statistically different because we can see this confidence interval intersects with 0. Right, so finally, remember at the beginning when we looked at this diagram, this is the diagram showing the actual data. What we said was, yes, we can see that these groups have different mean values, but we cannot tell just by looking at this graph whether the difference in these mean values is just due to sampling variability, in which case it's possible that the population mean responses, all 4 of them, are actually the same, or if the population mean responses are actually different and that the difference between mean values here is a consequence of those real differences. Well, now that we've done the analysis and we've rejected the null hypothesis, we can say that our analysis shows that the population mean response to treatment 2, right, we're identifying treatment 2 because of the multiple comparisons. So treatment 2 is greater than that for the other treatments, including the placebo. So that we're saying again is that the ANOVA tells us some of the population mean responses are different, and the multiple comparison tells us that its treatment 2 is the one that is better than everything else. And so what we would then say is to Dr. Helen Sharp that she should use treatment 2 with her patients in place of any other possible treatment. So I hope this sort of explanation has helped you understand these one-way ANOVA. If you have any questions, please just leave a comment and I will address that either in comments or I can send you an email or we can talk about it in class. Thank you for watching. Again, I hope this was helpful. I'll see you next time. Bye-bye.